Okay, let me introduce myself. I'm Brad Whitmore from the Space Telescope Science Institute, and I'll be hosting the next session, which is AI innovation. It's organized like the others. First have astronomy, then multi-message physics, and then high energy physics. And the questions will be held until the end of kind of after each three speakers in each little section. So our first speaker is Sankalp Gilda. Why don't you go ahead and share your screen? He's a graduate student from University of Florida, and he'll be talking about SCD fitting.
Hey everyone, can you all hear me?
Yes.
All right, perfect. Hi everyone. Like Brad said, I'm a final year grad student from UF. I'm presenting here a new Python-based tool that we've developed in collaboration with a fellow grad student Sydney and my advisor, Professor Deshika Narayanan. We're hoping, this is a kind of a big claim, but we're hoping this phases out traditional SCD fitting, and I'll try to make a strong case for it during the course of this presentation. So this is a fun slide. What this basically is: machine learning plus extragalactic astronomy. This is what's going to take us to the 21st century. Why is SCD fitting important? A few reasons. It is the primary way to derive galaxy properties from photometry. The amount of photometric data is larger than the amount of spectroscopic data by a factor of about 100. And using these derived galaxy properties, we carry a ton of scientific tasks downstream. I've just mentioned one example, differentiating a quenched galaxy from star-forming galaxies, because that's part of the thesis. Moving on, what are the drawbacks of this method and where is it lacking? A number of places. It's quite compute intensive. It typically runs on supercomputer nodes for several hours. This is complex Bayesian fitting with MC sampling. Even so, it's quite subaccurate, as I'll show you through plots, and it doesn't really account for it doesn't really account for all errors in a robust fashion. Without getting into the technicalities of what's in here, the important point to notice here is the non-parametric part. That's the current state-of-the-art SCD fitting star formation history model. I'm trying to show through this plot that the state-of-the-art non-parametric beats the parametric star formation history models, and that I am going to beat non-parametric itself. Another thing to notice, this is at SNR 50, and I'll compare results as low as SNR 5. I present Mirkwood. It has a number of properties. It's explainable, it's probabilistic, it accounts for both types of errors. I'll explain this in a bit. It's fast, it runs on my home machine in a matter of hours as opposed to running on supercomputers for days. It's very accurate as tested on simulations, and it's open source. We are very close to releasing our paper and our source code. This is another fun slide that I usually like to include because people have this misconception of this is what machine learning is. This used to be the case, I suppose, a while ago, but not so much. A lot of effort has gone into making machine learning explainable, as I'll show through plots. Quick overview of how this works. It's supervised ML. I have 3 sets of hydrodynamical simulations, Simba, Eagle, and Illustrious TNG, for a total of 16,000 galaxies. This is a proof of concept work, so we've only done z equals 0, and we try to predict 4 different galaxy properties: stellar mass, dust mass, metallicity, and instantaneous star formation rate. The reason to use 3 different simulations is to try and cover as much ground as possible in terms of parameter space. An overview of how Mirkwood works. In the interest of time, I won't spend a whole lot of time on this, but basically we have 5-fold validation. A few differences from the various pipelines that have been presented in this conference so far is I estimate both types of errors, epistemic and aleatoric, which are systematic And statistical, for this, I carry out bootstrapping. This is difference number one. And difference number two is I carry out something called calibration, because machine learning models typically are overconfident in their predictions. So you have to sort of bring them back to reality. Quick highlight of what epistemic and aleatoric uncertainties are. Epistemic certainties are statistical ones, which are high in regions of parameter space where you don't have a lot of data. And aleatoric is inherent error in the data. In this case, it derives from, say, the SNR of your input data set. A low SNR will give you high aleatoric uncertainty, and vice versa. Here are some results. At SNR 5, I'm trying to compare results at a very low SNR to show the benefit of using this method over traditional SCD fitting. This is, y equals x line. This is for mass, log mass, and I've used 3 different metrics to compare performance. As you can see, we are just visually and quantitatively doing significantly better than the current state-of-the-art method. Similar results for dust mass. Similar results for metallicity, though you will notice that compared to the first 2 plots, our metallicity results are not as accurate, not as tight. And this is a known fact. Mass is the easiest property to predict, and everything else is in a bit dependent on it and not quite so accurate. And this is star formation rate. Here we see the biggest delta between our method and the traditional SCD fitting using non-parametric star formation histories. Here I compare our predictions in terms of error bars. This is non-parametric. This is Mirkwood uncalibrated. This is Mirkwood calibrated. I use 2 separate metrics. One is called fraction of the true quantity within plus minus 1 sigma of the predictive quantity. And the second is interval sharpness. This quantity says that for a really well-calibrated model, this number should be about 0.6827, which means if you have 100 predictions, about 68 of them should have the true value within plus minus 1 sigma of predicted values. And interval sharpness says that the model cannot achieve this goal by trivially expanding all error bars to infinity. The error bars should still be tight. Both of these values should be as high as possible. And here we show that our values beat the traditional non-parametric methods, non-parametric SCD fitting method by a significant amount. And that there is a benefit to calibration if you compare Mirkwood uncalibrated with Mirkwood calibrated. This is the only point where we are a little disappointed. This is something I'm exploring still. Why in the case of predicting metallicity, we're not doing as well as we do with traditional SCD fitting. But overall, the trend is quite definitive. This method just outperforms traditional SCD fitting, both in terms of predicting point predictions and error bars, PDFs.
I think we should finish up. We're getting a little behind.
Okay, just quickly, these are Sharpe value plots. We've been able to show that we derive feature importances that we would expect from domain expertise. For example, with mass, we know that K and H bands are the most important for predicting mass, and we've been able to rederive this in a completely data-driven way. The other 3 plots are quite similar. Dust mass, metallicity. We have quite an overlap with the plot for mass because of the well-known mass-metallicity relationship. And finally, star formation rate. Paper should be out very soon. Thank you for listening to me. If you have any questions, please feel free to email me at that email address. Thank you.
Okay, thank you. The next speaker is Matthew Graham. He'll be talking about alert streams. He's a faculty member at Caltech.
Hello. Let me just get PowerPoint up and running. So I'm the project scientist for the Strictly Transient Facility. This is a current sky survey. We've just entered the second 3-year phase. It's about a 10% LSST, which is of considerable interest to a number of the astronomers and MMA folks on here. We are about 50% public, 50% private data, in that we have funding both from NSF and also from member partners institutions. So ZTF is about 4,000 square degrees an hour. We can cover to a depth of about 20.5 with 30-second exposures. We've already put out about 90 papers over the last 3 years and 3 data releases, which have given light curves of about 5 billion sources. So as I say, we're about a 10% LSST in terms of data volume. Specifically, we put out a real-time alert stream each night of somewhere between 500,000 and 1 million alerts. Again, that's sort of 10% LSST, and so we've put out about 300 million alerts to date. Now, this whole area of managing the LSST alert stream or managing the ZTF alert stream is predicated on a couple of false assumptions. There's this usual idea that if you're developing a brokering system for this to handle these alerts and find the rare things and whatnot, you need a supercomputer or a dedicated cluster. You sort of say, well, I need to be able to connect to the full fire hose, get all, 1 million or 10 million alerts a night. I need to persist everything, and I need to have a local copy of all those big data sets out there in the astronomical community locally. And I think this is all wrong. And so the approach that we've taken at Caltech is to actually try and employ edge computing or an edge computing paradigm to come up with a lightweight decentralized approach where you don't need to be using any of that. Specifically, we focus very heavily on having machine learning or AI-based components where possible, and using commodity machine learning accelerators for fast inferencing. So, for example, I don't know if you can see this little chip that I'm holding up here. This is a $45 chip from Corel, and it has 2 edge TPUs on it with a combined computing power of 8 trillion operations per second. And that's used for really fast inferencing in sort of Internet of Things is the idea. Your smart fridge, your self-driving car. You can put one of those on a Raspberry Pi board for $50. You can get a 5G networking card for that for another $50, and you can get a $100 SSD thing on that, and you have something which is as performant as the cluster down in your basement in terms of doing fast inferencing. So what happens if you have a whole load of those together and you start doing fast AI-based alert distribution as well, so that people who are interested in white dwarfs get the things that look like a white dwarf, and people who are interested in doing solar system objects get those, and those who want supernova get those. You have a distributed system, and you can also bring federated learning to bear on this. So instead of bringing the model to the data, you bring the model to the data instead of the data to the model. So I don't even now need my big supercomputer to do the learning. I can do all the learning in this decentralized distributed fashion. I can make use of people's own access to heterogeneous data that maybe they can't share with the community, and to do specialized learning on specific things that they're working on using these devices, and then those all contribute to a global model for classification or whatever the thing I'm interested in doing. So that's what we're trying to develop, and that's what we are developing to handle this sort of data stream. So in summary, volume, velocity, variety of time-domain data is presenting us with new challenges in astronomy and MMA, but this traditional computing approach to handle event streams just doesn't work. It's not optimal. You don't need a supercomputer, or you don't need access to a supercomputer. You don't need a big compute resource, etc. You can do it with decentralized networks of low-cost, off-the-shelf components, which are employing commodity AI accelerators and reusable models. So one of the things I mentioned in the uploaded talk is this idea of TensorFlow Hub. I don't even need to train my model. If someone else has trained a model, I can just pull it off the shelf and then do federated training or just transfer learning specifically for my data set or my data stream. That way I reduce response time, I save bandwidth, and I can contribute to an overall system in a very cheap way. what's really important about this is it also democratizes access to the data and to the science. It's not just the big institutions who can afford the supercomputers who can do this. Anyone can do this. You can do this in high schools. You can have high schools contributing to real-time discoveries of supernovas or asteroids or whatever, right across the board. And it's, your total cost for a system is maybe less than $1 a day. So I think, we're missing a whole thing by not exploring or putting a stronger effort into this sort of decentralized approach. And I think it's a very viable way forward for LSST and for other big computing or big event data streams. Okay.
Okay, thank you very much. Let's see, let me remind people that there are the 15-minute talks that people should go listen to if they're particularly interested. And if you have some questions that are coming up, you can put them in the chat, or you can just go ahead when the time comes and open up and talk about it there. Okay, our third and last speaker for the astronomy section is Peter Yoachim from faculty member at University of Washington. He'll be talking about scheduling the Rubin telescope.
Okay, can you see me?
Yep, looks good.
All right. So we've heard a lot about LSST or Rubin Observatory already, and so I'm going to talk about how we're planning to schedule this thing. So the very quick intro, Rubin is an 8-meter telescope on Cerro Pachón in Chile. We're going to have a 3.2 gigapixel camera that's down here, about the size and weight of an SUV. We expect around 10 million alerts per night, generating 20 terabytes per night and 15 petabytes after 10 years. And so that comes out to about 800 observations, 30-second observations with this camera per night. And so we need to address where exactly we should point the telescope, because if we don't point it intelligently, that would be bad. We've realized we can't cast this as an optimization problem. Usually when you're scheduling a telescope, you have a single science goal that you're trying to optimize. So for example, with the Kepler Space Telescope, you're trying to optimize the number of Earth-like planets you find. Here, we're doing a general survey with multiple science objectives. And so we've ended up turning to a Markov decision process to kind of balance the three main things we need to do when observing. So we need to keep our slew time down. We want to get images as deep as possible, and we want to keep our survey footprint fairly uniform. And so we do the Markov decision process lets us manually construct basis functions based on these three desires. And so here's kind of what these basis functions look like when we run a simulation. We have our survey footprint, and so we take what we have surveyed minus what our idealized survey footprint would be, and that gives us one basis function. Another is looking at the 5 sigma depth in each filter across the sky. And so I'm doing this in an alt-az projection. So zenith is the center. And then we difference this with what the best possible 5 sigma depth would be. And so in this particular snapshot, the moon is down. And so this basis function is telling us we should observe on the meridian, which is correct. Then finally, we have a kinematic model of our telescope to figure out how long it would take to slew to different positions. And so if we can observe somewhere near where we're already pointing, that's good. If we have to spin our big dome 180 degrees, that's bad. We also include some masks and things. And finally, these sum together to give us a final reward function. And so you can see over on the right, there's areas where we've already surveyed this area and it's at high air mass, so it has very negative reward. And then over here, there's something just starting to rise up near the meridian that we haven't observed at all, and so that has the highest reward, and that's what the scheduler will decide, oh, this is the area I would most like to observe. And we're doing this in 6 filters, and so it will intelligently pick redder filters when the moon is up and things like that. So the nice thing is this gives us just 3 free parameters that we can adjust and tune to get our behavior. So it's a very low dimensional space to explore and optimize. After 10 years, we get 2.2 million observations, and this is what the survey looks like. So we have a wide, fast, deep region. We look at the North Ecliptic Spur for solar system objects, the galactic plane, and the South Celestial Pole. This is very close to the input desired footprint we wanted, so that was successful. We can look in alt-az space, and you can see here's where the telescope ended up pointing, and it is doing a good job. Because we're an alt-az telescope, we can't point at zenith. That would be a great place to look, but we can't physically point and track through there. So we're very rarely chasing observations to high air mass. We're doing a good job getting deep observations. And now that we have this framework, we've run a large series of experiments to try to, test different science cases and do different things. So for example, on the left here is our baseline simulation after 10 years and one snapshot year. And then we go ahead and change up the footprint to base it on extragalactic dust extinction, and also do what we call rolling cadence, where after 10 years, it looks nice and smooth. But on a given year, we'll have declination bands where we're emphasizing the observations. So kind of half the sky will have very well sampled light curves, and then the next year, the other half of the sky will get well sampled cadence. We have a large framework that we've put together for analyzing the output of these simulations. And so, for example, here we can look at how many galaxies we expect to see across the sky. This is incorporating dust, so dusty regions, we don't find a lot of galaxies, and so on. We also run a series of Monte Carlo simulations. And so here we simulate 10,000 microlensing events and see what fraction of the microlensing events we would recover given our survey parameters. And so you can see, the bulge, the LMC, and the SMC jump out here. And so as we change the coverage of those regions of the sky, we can say how much better or worse we're doing for different science cases. All right, so conclusions. We have an AI that uses a decision tree and Markov decision process to schedule the Rubin observations. We've released about 200 simulated surveys, and many of which were based on a call for white papers. And the survey strategy is still in active development. The full survey operations, we think, are going to start in 2023. Obviously, COVID is making things hard to guess. We have a message board, so if anyone has ways, things you think we should point Rubin towards, or want to help us measure the science cases for the simulations we have, please join in. And there's a big report on our release surveys. Thanks.
Thank you. Okay, we're open for questions. You can either send them in the chat or just open your mic. I've got maybe one for Peter while other people are thinking of their questions, which is weather. Do you try to track weather in any way? I mean, as a front comes in from the ocean or something and it covers that part of the sky, do you try to avoid that?
So we're simulating weather downtime in our in our simulations. We have a historical record, so we shut down. We have considered having an all sky camera where we look at the stars that are up and see where the clouds are coming in and feed that map in. Our colleagues in Chile tell us that usually it's either completely clear or completely cloudy. It'll be a very, very small fraction of the time where we actually have to chase sucker holes. So it's something we're considering, but it's not the top of our optimization list.
Okay. Other questions, please?
Hey, I have a quick one. Peter, you said during the beginning of this talk that you guys made a conscious choice not to frame this as an optimization problem. Could you expand on that a little bit?
Right. It's previously folks were really focused on, say, optimizing the slew time, just keeping the slew time as low as possible. And if you do that, it turns out the best way to do that is point the telescope at very high air mass and just raster an azimuth side to side. You have very short slews, but you're looking at an air mass of 2 every observation. And it turns out with the Markov decision process, if I turn up the weight on any one of those parameters too far, it really ruins the other 2. That's why I have that standoff image. And similarly, if we try to only care about image depth, we'll end up slewing around and filter thrashing a lot. Rubin Observatory takes 2 minutes to change filters. And so it's this balance that we have to do.
Couldn't one argue in that case that it's just the loss function that was improperly created? You could still do optimization, but with a different loss function?
The question is, what do you optimize? And in the end, what we really want to optimize is science. And so we would need some kind of conversion factor to say how many supernova equals an asteroid equals a microlensing event. And so it's not clear what the units are that we would be maximizing.
Got it. Thank you.
Other questions? Oh, here's from John Wu. Why don't you open your mic and ask your question?
Sure thing. Yeah, really interesting stuff, Peter. I just wanted to check, with people interested in measuring correlation functions or galaxy clustering and stuff like that on large scales. Is there any way to also factor that sort of stuff in? I might imagine something in the Fourier domain of in terms of, what kind of slews or steps that you would take?
Yes, so this was also an issue with the previous version of the scheduler. Dithering is really important, and so what we've done is those basis functions I was showing are computed on a Heel pixel map at a higher resolution than the Rubin field of view. And so every night we have a tessellation of the sky that we randomize the orientation of that tessellation and use that for the night. So basically that's why we're getting very, very smooth maps at the end. We're getting very close to perfect dithering. So yes, we're very worried about large scale structure, power, leaving those residuals in there. So we're trying to dither as well as we can.
Let's see, there's also a question from Michael Coughlin.
Sure. Yeah, Matthew. Do you want to summarize from your perspective the whether we're ready for the, let's say, order of magnitude increase in data going from ZTF to LSST in terms of sort of the science readiness that you talked about computing with?
Yes, we are. I think it's a complete misnomer that we're not ready. ZTF is running at 10% and a 10% scale up. I mean, we can do full alert processing with a not too powerful computer desktop. And so I think this whole idea of we should be scared of the fire hoses, I think, it's a legacy idea from about 20 years ago. Our computing requirements have vastly increased. The other thing is, as I think I said in the recorded talk, that yes, you are putting out 20, 30 million alerts a night, but most of those are coming from variable stars, which are things we know about. The actual things that are going to be changing and interesting is a much, much smaller fraction of that. And so the effort really has to be in the filtering and identifying the things that are interesting. And I think that's where really fast machine learning inferencing is where you get your dollar's worth, quite literally in the case of the solution that I'm proposing. But I think these ideas that we need, this sort of stuff is not, the bigger problem is actually the follow-up. And say, so yes, you've detected something interesting. What are you going to do now with that from the perspective of science? What do you do if you've found a 25th magnitude supernova? What do you do if you think you've got a faint asteroid which is out, past the orbit of Pluto or something like that? You need non-computing resources to do that, and that's where I think we put the bigger problem. But that's outside the purview of this particular conference.
Okay, I'm afraid we need to move ahead. So let me pass it over to multi-messenger astrophysics.